Welcome to The Explainer. Today we are jumping into a topic that's fundamental to physics and, yeah, a huge part of the O-level curriculum, the general properties of waves. So whether you're studying for an exam or you're just a little bit curious, let's break this all down. I mean, just look at the power in that image. You can almost feel the energy of an ocean wave, can't you? It's strong enough to reshape an entire coastline. But here's the fascinating part. This isn't just a giant wall of water moving across the sea. It's actually something much more subtle, a massive transfer of energy. And that leads us to the central puzzle, right? If you imagine a seagull just floating way out at sea, it just kind of bobs up and down as a wave passes under it. So how does the energy from that wave travel hundreds of meters to finally crash on the shore? This is the core question we are going to answer. Okay, so here's our game plan. We'll start with the absolute basics. What even is a wave? Then we'll look at the two main ways they move, we'll learn the specific language scientists use to talk about them, and we'll uncover this one simple but super powerful equation that governs them all. And then finally, we'll see how these ideas pop up literally everywhere. First things first, we need to get a really solid grip on the most fundamental idea behind every single wave. Doesn't matter if it's in water, in the air, or even light traveling from a distant star. Imagine you're holding one end of a really long rope. You give it one good flick. You see that ripple, that wave, travel all the way to the other end. But if you look really closely at a single point on that rope, like point A here, what's it doing? It's just moving up and down. It oscillates, but it doesn't actually travel down the rope itself. And that is the crucial point. A wave is an energy delivery system, not a matter delivery system. It's a disturbance that moves through something, carrying energy with it, but the stuff it's moving through, we call that the medium, like the rope or the water. It pretty much stays put. And this illustrates that idea perfectly. Think about a leaf just floating on a pond. When ripples from a stone you dropped reach it, that leaf doesn't get carried all the way to the edge of the pond, does it? Nope. It just bobs up and down as the wave passes underneath. This is perfect proof that the water particles themselves are just oscillating, while the energy is what's traveling outwards. So let's move on and see how this energy transfer actually happens. It turns out there are two fundamental ways that particles in a medium can oscillate, and that gives us two basic types of waves. So on the left, we've got that familiar up and down wave on a rope. On the right, we've got more of a push and pull wave in a spring, like a slinky. They look completely different, and that's because the particles are moving in fundamentally different ways compared to the direction the wave is traveling. And here's the key difference. In a transverse wave, the particles vibrate at a right angle, or perpendicular to the direction the energy is moving. The best way to picture this is the wave in a stadium. People stand up and sit down, but the wave moves sideways. In a longitudinal wave, the particles vibrate back and forth, parallel to the direction of energy. Sound is the classic example of this. Okay, so now that we know what a wave is and its two basic forms, we need to learn the specific language, the correct scientific terms, to describe them precisely. This is like getting the blueprint for any wave in the universe. This diagram basically is that blueprint. It has all the key terms we need, so let's just break it down piece by piece so it becomes second nature to you. First up, amplitude. This is really just how big the wave is. It's the maximum distance a particle moves away from its resting position. So a bigger amplitude means more energy. For a water wave, it's just the height from the calm water level right up to the very top of a peak. Next is wavelength, which we represent with the Greek letter lambda. And just like the name says, it's the length of one complete wave. The easiest way to measure it is from the top of one wave, its crest, to the top of the very next crest. And speaking of which, those points have their own names. The highest points are officially called crests, and the lowest points are called troughs. Simple as that, crests and trough. Now, this is where it gets really interesting, how we draw these on a graph. This is a displacement distance graph. The best way to think of it is like a photograph of the entire wave, frozen at one specific moment in time. It shows you the position of every single particle all along its length. But this graph is different. This is a displacement time graph. So instead of a photo of the whole wave, it's like you're recording a movie of just one single point, like our leaf on the water. And you're tracking its height over time as it moves up to a crest, down to a trough, and then back again. So really think about that distinction. The snapshot, the distance graph, clearly shows you the wavelength. The time graph can't. But the time graph, the little movie, can tell you how long one full oscillation takes. Understanding this difference is absolutely key. All right, let's connect all these new terms we've learned, wavelength, amplitude, time, with one incredibly powerful and really elegant equation that just ties everything together. So first, we need two more related ideas, which we can actually get from our displacement time graph. The period, with a capital T, is just the time it takes for one complete wave to pass you by. And the frequency, little f, is how many complete waves pass by every single second. And as you can see, they are just inverses of each other. And this brings us to the master formula. Wave speed equals frequency times wavelength. And it makes perfect sense when you think about it. How fast the wave is traveling has to depend on how many waves are passing by per second and how long each of those waves is. This is one of the most important equations you're going to learn in this part of physics. So why does any of this matter? Why are we learning about crests and troughs and this equation? Because this blueprint, this language of waves, applies to an incredible range of things that shape our entire world and even the universe. Everything you hear is a sound wave. Everything you see is a light wave. Earthquakes travel as incredibly powerful seismic waves. Medical tech, like ultrasound, uses these exact same principles. And what's really amazing is that scientists can even study the tiny electromagnetic waves produced by our brains to understand how we think. And this is the big takeaway. This is not just a topic for an exam. Understanding waves is like learning a fundamental language that describes the universe. The fact that the same simple rules, the same exact equation, can describe a tiny ripple and a powerful signal from a star, well, that's just a beautiful example of the underlying simplicity and order in physics.